So now it's my pleasure to introduce our lunchtime keynote speaker, Dr. SyracuseCoE Harris. Dr. Harris is a Science and Technology Policy Fellow at the U.S. Department of Energy's Building Technology Office. His current focus is on the development of an analysis tool to evaluate the impact of new technologies on the energy and carbon footprint of the building sector. He also helps guide R&D for windows and opaque envelope technologies, in addition to supporting a wide array of emerging technology programs. Dr. Harris was most recently a postdoctoral fellow at the University of Texas at Austin, where his research focused on the optimization approaches for vehicle-to-grid systems and solar PV configuration models. He completed his PhD in mechanical engineering also at the University of Texas and also on vehicle-to-grid. He participated in home energy use research initiatives related to plug-in electric vehicles with the Pecan Street Research Consortium, also located in Austin. So he's got a wide variety of experience in the energy industry. Before that, Dr. Harris served as an energy and climate change program intern at the Council of Environmental Quality at the White House. He also has worked at Boeing on several programs, including aircraft landing gear systems, satellite launch vehicles, and space shuttle propulsion and power systems. He received his MS in mechanical engineering from University of Texas at Austin and a Bachelor's of Science in Mechanical Engineering from Brown University. So join me in welcoming Dr. SyracuseCoE Harris from the U.S. Department of Energy.
Thanks, Chetna, for that introduction. So as Chetna mentioned, I'm a AAA Science and Technology Policy Fellow at the U.S. Department of Energy in the Building Technologies Office. Today I'm going to be talking to you a little bit about the Quadrennial Technology Review, which is what I was asked to speak on, and I'll also be talking about some findings related to the QTR, as well as funding opportunities that are linked to both tech-to-market initiatives and also broader funding initiatives that might be appropriate to a lot of the people who are here in the audience today. So first, a little bit of background about the quadrennial reviews that the Department of Energy conducts. The first main review is the Quadrennial Energy Review, or QER. The QER is a review conducted in theory every 4 years, although what they've done to make it easier to actually conduct the review is they've split it into 4 parts. And it's primarily focused on energy infrastructure in the United States. So that's both energy delivery, in terms of systems like the electric grid, as well as petroleum-based fuel delivery systems. The other major quadrennial review, as I'll be talking about more today, is the Quadrennial Technology Review. That's conducted every 4 years as a single report, and that review was aligned with the start of the process for the QER so that we could have those kind of structured in lockstep. And it focuses primarily on the technologies that underlie the energy potential, energy use, and energy savings opportunities that exist in the US, as well as R&D frontiers that are being explored by the various technology offices at the Department of Energy. So the report not only informs the future plans for a lot of the technology offices at DOE, but it also sets a sort of current state of the art and current baseline in terms of technologies that are employed in the energy system today. So the last QTR was 4 years ago, and in the past 4 years, we've seen enormous changes in the energy landscape in the United States. One area of significant change has been in the introduction of systems like hydraulic fracturing that have really changed the landscape in terms of oil and gas production in the US. Our oil and gas production has exploded over the past 4 years, and energy prices in the oil and gas sector have correspondingly changed as well. There are also international factors that have affected oil and gas prices, that have affected consumers in terms of their purchasing decisions and buying patterns. We've also put in place plans to increase light-duty vehicle fleet mileage over the course of the next decade or so. And we've seen huge deployments, huge scale-ups in both wind energy and solar energy. And those are associated with both improvements in technology as well as reductions in cost for those various technologies. We've reduced electricity demand growth, and we've seen a corresponding reduction in CO2 emissions, or corresponding trend in CO2 emissions nationwide. The potential over the course of the next 4 years until we do a QTR again is that we'll see, I think, continued growth in advanced energy technologies and corresponding reductions in costs associated with the programs that we have in place, as well as programs through organizations like NYSERDA to support advanced energy technology R&D that will improve the performance and cost of those technologies. And I'll talk more about some of those technology opportunities a little bit later. So I wanted to give a little bit of background on some of the technologies that we've seen significant changes in the past 5 to 10 years. So the 4 that I highlighted here are land-based wind power. And here you can see the trend is since 1980. So it's a little bit of a longer time horizon than some of the other figures shown. But you can see as the costs come down initially, there's big changes in costs associated with R&D advances, but there isn't really significant adoption. And then they reach a point in the price curve where the cost is low enough that you start to see significant adoption in sort of the mid-2000s. And since then, growth has really taken off. Cumulative installed wind capacity has grown quite significantly, and particularly in places where there's a significant wind resource. Work that's been done to characterize the quality of wind resources across the United States has enabled states to put in place appropriate incentive programs to catalyze growth in the installed wind capacity in those states where those wind resources are really high quality. In addition, we've seen many other presenters have actually mentioned this, huge changes in the cost of LED lighting. So over just the past 7 years, the cost of LED lighting technologies has dropped by an order of magnitude. And similarly, you see a huge growth in the installed capacity or the install base of LED lighting across the US in both the residential and commercial sectors. Electric vehicles over a similar time horizon, since they've been reintroduced to the market nationwide, have seen significant growth nationwide as well as international sales growth. And finally, solar PV. Here I showed distributed generation. There's a similar figure that you could show for grid scale installations as well, where over the past 5 to 7 years, there's been a significant reduction by about half in the installed cost for solar PV for both distributed and grid scale projects. And similarly, we've seen consistent year-on-year growth in the total or cumulative installed capacity for both grid and distributed scale systems. So how did we actually get to the QTR? The QTR is a huge document. It's over 600 pages long. So how did we end up with a 600-page document? Well, there's a lot of things that fed into that process. Obviously, there were a lot of authors involved from all the different technology offices. And a big part of the effort actually fed through the analyses that individual technology offices are doing on a regular basis to support their own programs. So the 2 reports that are shown on the screen actually come from my office, the Building Technologies Office. But they're 2 of the many reports that even an individual technology office will do to help support and guide their own R&D programs. So even within a technology area like power generation or buildings or manufacturing, there are many of these program plans, technology reviews, and roadmaps that are conducted to help guide their own programs, but then those fed into the QTR. And sort of as that process continues, when we author the next round of QTR, we'll have a whole new set of updated roadmaps that we can use to feed into that process. And then, of course, as we moved towards a finished document, we did a lot of work coordinating with leadership, coordinating with the White House to actually get everyone sort of on the same page in terms of the findings that we have that are in the QTR, making sure that everyone is up to speed, everyone in leadership is up to speed on all the findings that are covered in the QTR and the sort of headline findings, and I'll talk a little bit more about some of those findings that are relevant, I think, to this audience in a little bit. So for those of you who are not familiar with this figure, it's a Sankey diagram of the energy sector in the United States. So on the left of the figure, you'll see the energy sources in the US. So those are things like solar energy, wind, nuclear, et cetera. In the middle, you'll see the sinks. So those are the residential, commercial, industrial sectors, and transportation, the 4 major users of energy in the US. And then all the way on the left, you have that broken out into energy used to provide services, and then energy lost through various losses, usually as heat. And then in the middle, there's the electric grid. And this is essentially how the report is constructed. The QTR is based on the supply side, the demand side, split into buildings for residential, commercial, manufacturing in the industrial sector, and then transportation. And then finally, a section on the electric grid. And I'll talk about findings from each of those areas in a little bit. One big thing to note here is the time scale difference between supply and demand side. And this is a really critical thing when you're thinking about the findings that are discussed in the QTR for these various aspects of the energy system. The time scale for change and growth in the petroleum, for example, production and supply side is very different. That tends to be large capital costs, significant infrastructure commitments for a given fuel type or for a given product. So the timescale for change in that sector is going to look very different than something like the transportation sector, where vehicles are being replaced all the time. So when you think about efficiency improvements, technology changes that are happening in these various areas, you need to keep in mind the differences in timescale associated with the different parts of the system. Another thing to consider here as well, and I don't think I'm going to get to this at any later point, but it's kind of important to consider, is that some of these sectors are highly dependent on a single source fuel. So this is particularly true in transportation, where almost all of the energy for transportation is coming from petroleum products. So if you want to have an impact on petroleum use in the US, and you want to do something on the demand side, you probably should be working in the transportation space. Similarly, if you want to have an impact on electricity usage, you probably want to be working in the residential commercial sectors because they're the primary users of electricity. So depending on where you want to be operating in terms of your technology development, that should be based on which sector is the primary user of those input fuels or energy sources. So the findings in the QTR are broken into a couple of key groups. I actually made up these groups. These are not the official groups for the QTR, but I looked at the findings and I realized that there's sort of these core areas where they had these very high-level findings. The first one is in the electric grid. The changes that we've seen over the past couple of years and the changes that we foresee over the course of the next 5 to 10 years are centered around modernization of the delivery system. And this is something that we saw earlier today in the discussion. A lot of presentations have focused on changes in the delivery system that need to happen to make the delivery system both more efficient, more effective, and maintain reliability, or if possible, improve reliability from the existing operating state today. In addition, we're going to see continued growth in the deployment of clean generation technologies. So that's primarily wind and solar, but also growth in geothermal. We're continuing to do work on subsurface technology improvements to improve both geothermal small scale and also large scale grid scale facilities as well. Tidal power and some of these other marine hydrokinetic power, some of these other power sources that are currently still very much in the R&D stages, but could be significant players in the future when we're talking about low or zero carbon generation options. The next major area is in energy efficiency. A key area for improving energy efficiency is going to be in the building sector. Both residential and commercial buildings offer significant energy savings opportunities and very durable savings opportunities in the future, both with technologies that exist today as well as technologies that are currently under research and development. And then also technologies that improve the performance and efficiency of manufacturing. Manufacturers have a significant incentive to improve the performance and efficiency of their facilities, and technologies that enable that process, enable them to improve the energy performance of their manufacturing processes, can have a huge impact on energy use, both direct and indirect through grid power. Finally, in transportation, both cleaner fuels, so making fuel production more efficient and cleaner throughout the supply chain, as well as improving the performance of vehicles themselves through either moving to different power sources or moving to more efficient combustion approaches that utilize existing fuels more efficiently. And then finally, enabling science and technology. And what that means is all of the basic science research and technology development that underpins a lot of this applied science research and finally commercialized products. So that may be in the areas of data management, computation, data center design, and kind of those areas where computing and research foundations really enable the development of these technologies that we're talking about when we're talking about the energy sector. There's also a lot of cross-cutting initiatives that are discussed in the QTR, and these are areas where multiple technology areas are impacted by the research and development that are occurring in these areas. The cross-cutting areas that are talked about in the QTR parallel cross-cutting teams that exist within the Department of Energy. So in each of these technology areas, whether it's energy water nexus, subsurface science, as I mentioned before, or energy storage, these are technologies that have impacts across different sectors, and as a result, all of these different technology areas have their various program management and staff coming together to make sure that they're doing a coordinated effort, both in terms of program planning as well as R&D support to make sure they're maximizing their R&D dollars. So as I mentioned, I wanted to talk about a few specific technology area and cross-cut area highlights just from the QTR. and from some of those roadmaps. The first has to do with the energy-water nexus. So this figure is part of work that's been done by the Water Energy Tech team, which is one of these cross-cutting teams at DOE. This is work that's been done by Lawrence Livermore and Lawrence Berkeley National Labs to characterize the energy-water system, first at a national level, and now they're working on characterization at the state level. So each individual state will have its own sort of energy-water system characterization. This figure shows essentially the same type of Sankey diagram that you saw a few slides ago, except now the water use associated with a lot of those energy components or energy elements is added into the system. And I want to bring your attention to a couple of key areas. The first is the use of non-traditional waters. And this is something that's a really huge opportunity, particularly in areas where there's a lot of groundwater resources that are relatively low quality, brackish water, where those waters can be used to provide services in sectors like power plant cooling or biomass fuel production or bioenergy fuel production, where high quality, clean drinking type water isn't necessarily required to support those processes. And there may be opportunities to use these non-traditional waters that may be readily available and have a lower energy footprint for that process operation. Another major opportunity is improving the water efficiency of bioenergy systems, and that's both in the field and actually at the production site where they're converting those bioproducts into fuels, as well as more water efficient cooling technologies. So both ARPA-E and Department of Energy offices are investing in research to support more water efficient cooling technologies, both for HVAC systems and also at power plants. Additionally, work on optimizing energy and water use in commercial and industrial systems, in a lot of cases process improvements, and as I mentioned before, changes in cooling technologies can offer significant benefits in the water use of and associated energy use of these various industrial and commercial processes. And finally, sustainable utility operations, so making water utilities in particular more efficient in their use and treatment of their water resources. Another significant area where we see cross-cutting opportunities is in grid design. As you all know, the historical system of centralized control, grid management, limit-setting control approaches that are based on offline, behind-the-scenes characterization of system operation is changing now and in the future to systems that are more flexible, more responsive, have greater awareness of systems that are more distant to the transmission and distribution system, all the way down to end users and end devices, as well as more real-time operations. And actually some of the enabling science and technology work that I mentioned earlier is kind of in this area of enabling near real-time and real-time operations to streamline performance and be able to handle with greater resilience interruptions, disruptions to the system, and maintain efficient operation over time. Energy storage is also a major player. Energy storage is a key enabler of wind and solar generation and other intermittent renewables. Energy storage remains challenging from a cost standpoint, so we continue to support R&D to reduce the cost of energy storage, and that's at a variety of different size and time scales. So not just energy storage that's suitable for, that's very high energy density, very short time scale, but also not as energy dense, but over a longer time scale. So systems like flow batteries, that are suitable for grid storage type applications are still a huge opportunity space and one that we're investing in. Apologies for the number of bullets on this slide. I really tried to get wind and solar onto one slide because I wanted to talk about them all at once. But wind and solar are areas of significant potential, and we've seen, as I showed a couple of slides ago, we've seen significant growth over time in both wind and solar generation, and we want to do work that will continue that trend. So wind was 4.4% of total generation in the US in 2014 and supports more than 70,000 jobs in the US today. But to be able to continue that growth and sustain that potential, there are pretty significant research and development opportunities that remain in terms of power plant site configuration. And this is another area where sophisticated computation can really come into play, where with more computing power, we're able to do a better job of characterizing the flow conditions in a power plant or a wind plant facility, and then use that information to do better plant design to re-optimize the layout of those facilities, particularly in response to more detailed input data with respect to wind characterization in various facilities. In addition, there's ongoing work to improve the design and performance of wind turbines. I think some of the work that's actually been presented at the poster session kind of gets to some of this work where through materials improvements, through design optimization, we can get significant performance improvements in terms of the efficiency of existing wind turbines. In the solar space, we've seen huge reductions in cost over the past couple of years. We now have module costs below $1 a watt, but there remain significant cost reduction opportunities in the solar space. A big area where we're currently trying to work is in what's called soft costs. And so that's essentially a balance of system costs. So in the chart that's actually shown on the screen, the green portion of the bar is the soft cost portion of the bar. The green and the orange, actually. So those represent costs associated with getting the solar facility, whether that's a grid scale facility or a distributed, like a rooftop system, associated with making that system happen, but they don't actually have anything to do with generating electricity. So those are things like permitting costs, installation, lead time, inventory costs, all of these costs that have nothing to do with actually getting electricity and are all just sort of programmatic and operational costs. And we're really trying to work to bring those costs down because they have nothing to do with energy generation, so that what you're actually seeing is a real cost for the energy and not paying for these sort of operational costs that aren't really getting us where we want to go. And then in buildings, there's significant opportunities. This is actually, the figure shown on the right is part of an analysis that I actually did that looked at the energy savings opportunity across a range of different technology scenarios. So we looked at the current building stock and compared it to technology deployment scenarios across a couple of different building types or building product cases. So we looked at and this essentially assumes a uniform complete deployment of these various technology levels. So we looked at the 2009 IECC building codes. We looked at Energy Star performance, current Energy Star technologies. We looked at the best available, so sort of in each different technology sector, whether that's HVAC, windows, opaque envelope insulation, and air sealing, what is the best available or best performing product that you can buy on the market today, but it's all commercial off the shelf, no R&D. And then finally, the thermodynamic limit, which was an analysis that was done by some of my colleagues to characterize sort of what is the best case scenario. And we had a couple of different findings from this work. One is that there's actually pretty significant savings opportunities just from technologies that are available today. They may or may not be cost effective. So Energy Star includes a cost effectiveness component to the selection of technologies and the setting of that Energy Star standard. But the best available is just whatever you can buy at any price. But if you bring the price down on those technologies, these are things that are off the shelf today. There's no R&D required. So there's huge energy savings opportunities just in that space, just by bringing costs down. So it's a huge area of opportunity in the building space. There are other areas where we're working in work that will actually help with global warming potential or CO2 equivalent emissions. So we deal with a lot of direct emissions associated with refrigerants, and we're currently working in collaboration with our international partners on bringing down or reducing the use of traditional or current HFC refrigerants, moving to low GWP, low global warming potential refrigerants, as well as looking at what we call not-in-kind refrigeration technologies or HVAC technologies. Those are technologies that don't use a refrigerant at all to provide heating or cooling. And so that's a huge area of opportunity for us where we're still doing continuing R&D, and we are hoping to see significant growth over the next decade or so. Finally, we have a bunch of programs that are ongoing that we use to move our technologies to market. So we do all this R&D to support these various technologies, and then how do we get those technologies sort of into the market, and how do we get people who have great ideas, how do we get their businesses off the ground? So we're doing a couple of different programs that I'm really excited about. One is called the JUMP crowdsourcing program, and that's where we're partnering directly with OEMs who have specific technology interests. So the three that we have running right now are shown on the screen. We have partnerships with GE, with UTRC, and with A.O. Smith to do this JUMP crowdsourcing opportunity where individuals can submit their ideas about technology development, and they essentially compete for a prize, and part of that prize is partnering with the sponsoring company to develop and deploy their technology. Another major opportunity that we're pursuing now is called the Catalyst Prize Competition. So we're currently in the middle of developing our current cohort of Catalyst Prize winners. Each Catalyst awardee gets $25,000 in software development services and then gets to compete for a $100,000 cash prize after being in a 2-month accelerator or incubator program. And so we've done that program now. We're on our second round in the solar space and our first round in the building space. And we're working on moving that to being actually an EERE-wide program. So across all the different technology areas that we work in, we'll have some sort of prize program like this. And then we also have a program called Cleantech University Prize, or Cleantech Up, which is a business plan competition that's similar in sort of structure to the Catalyst Prize. It includes an incubator component, and that is a regional-based program. And then finally, the Office of Technology Transitions, which is a newly formed office that was formed in, I believe, February this year, is focused on DOE-wide programs to support small business innovation and small business technology deployment. So we are currently running a program called the Small Business Vouchers Program. It's in its pilot stage, so it's our first time running it. And it allows small businesses that have a technology idea but need R&D support because they don't have the staff or the bandwidth to do all of the R&D they need, or they need specialized equipment or access to specialized resources. They can apply for assistance to the Small Business Vouchers pilot program, and they can then partner with a national lab that has the required expertise or the required facilities to be able to overcome those R&D barriers and get their product to a point where they can commercialize it. Finally, I wanted to mention, because this is sort of the thing that everyone gets really excited about when someone comes to talk from DOE, they're like, but where can we get the money? Where's the money? So this is the money part of the talk. If you go to these 3 URLs, you can find currently open and announced funding opportunities. That's from the Office of Science, from Energy Efficiency and Renewable Energy, and from ARPA-E. So all three entities within DOE provide various funding opportunities. Our office has one that's open now, and one that will be opening later this year. So one that's focused on small and medium commercial buildings, that's the one that's open now. And then we have one that's opening later. We've released our topics, and we include an open topic this year. So any buildings R&D related work you can propose to us. And then we also have a couple of specific topics that we're targeting as well. There's also the solar office, I know, has their current tech incubator. It's their 11th round of their tech incubator, and that's open until the 18th of this month. And there's a huge range. That's just a small slice of all the different funding opportunities that are open now through these various mechanisms. So I'd encourage you to check out those 3 websites and apply where appropriate. That's all. I'll take some questions.
So actually, I got us a little behind earlier, so we only have a couple minutes until the next sessions are supposed to start. Dr. Harris is going to be on our panel this afternoon at 4:15, so we'd like to reserve any questions until then, although I believe he's going to be sticking around, so you can talk to him before that as well. So thank you, Chioke.
Absolutely.